Hi guys, today is the last video for chapter 3, which is exciting. This one did get a little cut short because of our issues at the beginning of the semester, but everything's good now. This is going to be a longer video. All right, so energy is the capacity to do work. We already talked some about energy, but we're also going to talk about work. Okay, work is defined as a force over a distance. We're really going to talk about that next year in physics, so not as much this year. So the law of conservation of energy is exactly the same as the law of conservation of mass, but instead of mass, it's energy. So it says energy is neither created or destroyed. All you can do is change it from one form to another. Okay. Hopefully you remember from middle school kinetic and potential energy. Remember, those are the overbearing ones. So if you don't know, kinetic energy is the energy associated with motion. Potential energy is that energy associated with position or composition. So that's that stored energy. All other types of energy fall into those two major categories. So electrical energy, that's the flow of electrical charge. So that would be kinetic. Thermal energy, this one is important. You are going to need to know that one because that's one we're going to focus on this chapter. That's associated with the random motion of atoms and molecules in matter. Again, kinetic energy. And then chemical energy is a form of potential where it's associated with the position of the particles that make up a chemical compound. Okay, so that one is a potential energy situation. The unit of energy we're going to use is joules. That is the SI unit. The second unit of energy we're going to use is a calorie. Okay, and then a calorie is, sorry about the phone, y'all. So just remember that a calorie, we are talking nutritional calories. So there are two differences with that. There's a small calorie. That's the one we use for energy, small calories. And then big calories with the capital C, that's the nutritional one. And it's 1,000 of the little c calories. Okay, kilowatt hours. Some of you may have heard your parents talk about that with electricity. That's what the electricity bill is billed in, is kilowatt hours. So the meter on the outside of your house or your apartment, that's what that is. Okay, here is a table of energy conversion factors. I would make sure you either write these down or have this specific slide available for the test and the homework. All right, so we have a candy bar. I did not realize our transitions didn't come over very well. So they gave us 225 calories. We need to find joules. Notice these are capital calories. So first we have to get to small calories, and then we can convert to joules. Don't forget sig figs. We started with 225. We need to end, so that's 3. We need to end with 3. Okay, so they already worked that one. You seeing that one isn't super great. Okay, so we want 512 calories, and they want it in kilojoules. So we're going to do 512 calories times, remember, calorie has to go on the bottom, and we can go directly to joules because this is a small calorie. So 1 calorie is 4.184 joules. Cancel our calories. Okay, and then there's joules and kilojoules. And there's 1,000 joules in 1 kilojoule. So we do our math. 512 times 4.184 divided by 1,000. I get 2.14. That's kilojoules. Okay, so this is just some more practice. This isn't going to be heavily tested because we don't do a whole lot of this, but there'll be maybe 1 or 2 questions on the test about it. All right, so just remember potential energy is that stored energy either based on position, which is what it is in this image, or the composition, so what it's made of. So here we've got a position, it's up high, and at the bottom it's low. There we don't have as much potential energy. Okay. So as far as exothermic and endothermic reactions, I do understand that this is probably the first time you're hearing about this. You may have heard about it a little in bio. Maybe not. Exothermic means energy is released. So the reactants have more energy than the products. And endothermic means the energy is absorbed. The reactants have less energy than the product, so it takes energy to make an endothermic reaction happen. So, wood burning and ice melting. So wood burning is going to be an exothermic reaction. It's going to give off energy. But ice melting is going to be an endothermic reaction, which is kind of weird. No, that one's not weird. There are some that are weird, but ice melting should be okay. You do have to add heat to the solid ice to make it turn into a liquid. Freezing ice is the weird one. That one is actually exothermic. Because it is the opposite of melting, it has to be the opposite process. So it has to be exothermic. And that's why your freezer, it continually cools it. And that's why, because things are giving off energy in there. Natural gas burning is going to be endothermic. Sorry, exothermic. All burning things are going to be exothermic. Okay, as far as thermal energy and temperature goes, this is the one we're really focusing on in this chapter. So atoms and molecules that compose matter are in constant random motion. We already talked about that. Temperature is a measure of that energy. Temperature is not heat. Temperature is a measure of heat. Okay. Heat is the transfer or exchange of that thermal energy that's caused by a temperature difference. And again, temperature is a measure of the thermal energy, not the energy itself. So I'm not going to ask any Fahrenheit questions. You probably know the average body temperature, is between 96 and 98. You may know the freezing and boiling points at least you know the freezing point of water in Fahrenheit, because, when it freezes, we may not have school depending on the weather. But Celsius and Kelvin we will use consistently, so I really need you to know those. I also need you to know the boiling point and the freezing point of water in Celsius. You should know that already. Water freezes at 0 Celsius, water boils at 100 Celsius. Kelvin is the SI unit, and we did talk about that for temperature. So Kelvin we will use later on exclusively. This chapter we're going to focus more on Celsius. But I do need you to know that absolute 0 is 0 Kelvin. So 0 Kelvin. And that is when all molecules stop moving. That is important because that is the lowest temperature anything can go. So yes, those numbers can be transferred to Celsius and Fahrenheit, but they don't go below that 0 Kelvin mark. So here's just a scale. You notice that the Celsius and Kelvin scales have the same amount of degrees between freezing and boiling, but Fahrenheit is a different scale, which is why we don't use that one as much. So here are our formulas. You can get rid of 0.15. We can just do 273 plus Celsius is Kelvin. Okay, as far as Celsius with Fahrenheit, you do need to make sure the top is in parentheses because you have to do that first. Also notice Kelvin does not have a degree symbol. If you put it, I'm not going to count it wrong, but it doesn't have a degree symbol. It's just a K, capital K. All right, so we know that Kelvin is Celsius plus 273. So I do negative 25 plus 273. And I get 248 Kelvin. Okay, now we're going the other way. So if Kelvin is Celsius plus 273, then Celsius is Kelvin minus 273. Okay, by rearranging that equation. So I've got 358 minus 273. I get 85 degrees Celsius. Okay, y'all, let me know if you have any questions about this, but this is really not that difficult. All right, Fahrenheit to Celsius. So remember, Celsius is equal to Fahrenheit minus 32. That's a parenthesis. Sorry, it looks kind of weird. Divided by 1.8. Okay, so we've got 55 minus 32. Remember, you need to push equals or put in parentheses, and then we're going to divide that by our 1.8. So for degrees Celsius, I get, really, this should probably be 13 degrees Celsius. And there it is, 13 degrees Celsius. I'm not going to ask you any Fahrenheit questions on the test. However, they may appear on the homework. So Fahrenheit, this is just rearranged, is 1.8 times degrees Celsius plus 32. So I've got 1.8 times 139 plus 32, and I get 282 degrees Fahrenheit. Okay, this one does require 2 steps. So we solve for Celsius from Kelvin, and then we plug that into our Fahrenheit equation. So we got 36.85 Celsius. We plug that in and we get 98.33 Fahrenheit, or 98 degrees Fahrenheit. Okay, I'm not going to work another one of these. Just know that if you have to go through both, you need both equations. Again, I'm not testing Fahrenheit. I will only test Celsius and Kelvin. Next is heat. So heat capacity is very important. That is the quantity of heat required to change the temperature of a given amount of substance by 1 degree Celsius. And this is per each substance. Okay, I do want you to know the units for this will be joules per gram degree Celsius. And then the specific heat capacity, or the specific heat, is just specific to a substance, and it's going to tell you what substance it is. Okay, here is a specific heat table. You may need to mark down this slide because it's going to expect you to know some of it, and it's all from this slide. Okay, so on a test or a quiz, I would give you these numbers, but on the homework, it doesn't on Mastering Chemistry. Okay. As far as the equation, this is super important. Q is equal to mc delta T. Q is heat in joules. M is mass in grams. C is the specific heat capacity in joules per gram degree Celsius. T is temperature. This one will be in Celsius. And delta means final minus initial. So final minus initial. That applies to all deltas. They're always final minus initial. That's what change in means. So that triangle is called a delta symbol. Please do not call it a triangle. It's delta. It means final minus initial. All right. So we're going to do a problem. It says gallium is a solid at 25 Celsius. It melts at 29.9. It tells us the specific heat, and it says how much heat. So here's our equation. Q is equal to mc delta T. So Q is what we're looking for. Mass is 2.5 grams. It told us that. C, it also tells us 0.372 joules per gram degree Celsius. And then our temperature difference, because it's final minus initial, is 4.9 Celsius. Again, I got that from subtracting 29.9 and 25. I do want you to know, for some reason, at this point in the lesson, kids are like, how do I put joules per grams degree Celsius in the calculator? You never put units in the calculator. Please do not start now. I'm doing 2.5 times 0.372 times 4.9. That's it. So I get Q equals 4.6, and then the unit is joules. The unit is joules because my grams cancels, and so does my Celsius. Also, heat is in joules. Okay, that's the same question. Let's do another one. Notice it gave us a specific heat table. Tells us to find the heat capacity of copper on the table. So here's copper. We are going to use that. And it wants to know how much heat. So Q, does a penny absorb? Here's our initial temperature, final temperature, mass. So Q equals 3.10 grams. times 0.385 joules per gram degree Celsius times 37 minus -5, because remember it's final minus initial, which does give us 42 degrees Celsius, because that is the change. It's like a range. Think about the number line. So I've got 3.1 times 0.385 times 42. And I get 50.1 joules. Okay, let's do another one. We've got, here's our temperatures, absorbs heat. What is the mass? To get this, you do need to rearrange the equation. Okay, if you cannot rearrange the equation, just plug in what you have. You have 11.3 joules equal to mass. We don't know the mass. It tells us it's lead, so we go to our table, we find lead. And then our difference in temperature is 12 Celsius. So to get mass by itself, I need to divide by these numbers on both sides. Okay, it is very important that you put the bottom in parentheses, because if you don't, your number is going to be wrong. Okay, so mass is equal to, just looking at how many sig figs I need. I need 2 sig figs. It should be 1,100 grams, because it comes out to 1059. Oh, look, I didn't use parentheses. I typed it in wrong. It is not 1,100. 7.4. Yes, there it is. Okay, so look at the difference when you don't put it in parentheses versus when you do. Very large difference. Make sure you're paying attention to that, because you see what happens when you don't. All right, now it wants the heat capacity of rock. Okay, we've got a mass, we've got temperatures, we've got heat. So I've got 174 joules equals 14.3 grams times C times 52 minus 25 is 27. Okay, remember these have to go in parentheses. Please don't do what I did. So that cancels, that cancels. C is equal to 0.45 joules per gram degree Celsius. Okay, and it says, determine whether the value is consistent with gold. So we go to our chart. No, this is not gold. This is iron. Because look, iron is 0.449, which would round to 0.45. Okay, that is all I'm going to do. We've done a good amount. Okay. And then that's it. So if y'all have any questions, please ask. We will go through some examples in class. Y'all have a great day.